So once we figure out the enthalpy of reaction, we can actually do some pretty interesting calculations with this enthalpy of reaction. If you take a whole reaction and you multiply it by a factor, then you take the enthalpy of reaction and also multiply it by that factor. So, for example, we have carbon plus oxygen yields carbon dioxide, and we have an enthalpy of reaction already given to us that's negative 393.5 kilojoules. If we take that whole reaction and multiply it by 2, we now see that we have 2 carbon plus 2 oxygen yields 2 carbon dioxide, and we have our enthalpy of reaction is 2 times what it was at negative 787 kilojoules. So if you reverse a reaction, then the sign of your enthalpy of reaction is reversed. You just flip around the equation and you just flip the sign from negative to positive. Okay, so using these two rules, we can do some pretty interesting and useful things. There is a law called Hess's Law that says if you have to write a chemical equation as the sum of 2 or more steps, you can just add up the enthalpy changes for all the individual steps. And that's because it's a state function. It doesn't matter how you get there. It only matters where you start and where you end up. So we can do this to calculate the enthalpy of reaction for reactions that can't be done because of other reasons. So let's look at an example. I want to know delta H for the reaction 2 carbon, which is graphite, plus oxygen yields 2 carbon monoxide. But if I really ran this reaction, I wouldn't get carbon monoxide. I would get carbon dioxide mostly and a little bit of carbon monoxide. So what I want to do in order to figure out this delta H, this enthalpy of reaction, is I can take the delta H for each of these, right? Here's our carbon plus our oxygen, there's our carbon dioxide, and here's our delta H for that. But then if we take carbon dioxide and convert it to carbon monoxide plus oxygen, now we have our delta H as minus 566. So what we can do is we can add these two things together to get the desired reaction. So here's what we were originally given. The original equation that we wanted to use is 2 carbon plus oxygen yields 2 carbon monoxide. Okay, so in order to do this, we have to first multiply the first reaction by 2. So we have carbon, graphite, let me write it down over here. 2 carbon, right, plus 2 O2 yields 2 CO2. Okay, now we have a delta H that is twice this. So that is minus, I forget what it is, 787? Let me see if I can go to the next page. Yeah, minus 787 kilojoules. Okay, we go back one. So now we have minus 787. And if I take this second reaction, it pretty much is the way I want it to be. Okay, so if I just want to add it together, right, we already had 2 CO2 yields 2 CO plus O2. And my delta H here was minus 566 kilojoules. Okay, so if we add these reactions together, we are seeing that there's carbon dioxide on both sides. So we can already cross that off. And there's an oxygen over here, and there's an oxygen over here. So let's see what happens when we add it together. We have 2C plus 2O2 yields 2CO plus O2. Now, I don't have 2 of them on both sides. I have 2 of them here, and I have 1 of them over here. So what I can do is I can cross off one of these and cross off this one. Okay, so now we have 2 carbon plus O2 yields 2CO. And that is exactly what we were trying to get to up at the very beginning. So now we added these two reactions together, so all we have to do is add these two numbers. So it's minus 787 plus minus 566, and we get minus 1353 kilojoules. Okay, so we just added those two things up. Okay, it's kind of fun once you get to know these and once you get to learn how to do them, because they're like little puzzles kind of. All right, so here we see on the PowerPoint slides that it's canceling out the oxygen, it's canceling out the carbon dioxide, it's leaving just what we had, and we end up with our with our equation. All right, here's another one. What is the enthalpy of reaction for the reaction of calcium metal with water? I'm going to clear this screen. So let's see what we're trying to get. We're trying to get calcium plus water liquid yields calcium 2 plus 2OH minus and an H2 gas. Okay, so what the information that we do have is this. We have an H plus, we have an OH minus, plus H2O liquid, and we know that that one is minus 55.9 kilojoules. Okay, so that looks pretty good. We also know that we have calcium plus H plus yields calcium 2, and then hydrogen gas, and we know we have a delta H for that one. So, the problem that I see, the first problem, is that in the first reaction that we're given, our water is on the wrong side. This is on the product side, and we need it over here to be on the reactant side. So I know automatically that I'm going to have to flip this one around and change the sign. Okay. The other thing that I see is that once I do flip it around, I only have one OH over here. So I'm going to need to multiply that because we have 2 waters and 2 OHs, so I'm going to have to also multiply that by 2. So it looks like what we're going to have to do is just flip this one around and multiply it by 2. So let's keep going. Here's the reaction that we're trying to get to, and we identify each reactant and product, okay? And then we can tell right away that our water is on the wrong side and that our OH is on the wrong side, okay? And everything else looks pretty good. Okay, so let's reverse the first reaction to change the sign of the delta H. So now we've reversed it. Now our H2O is on the right side, okay? And we've changed the sign of our delta H here. Except, again, we only have one water here, and we need 2. And we only have one OH here, and we need 2. So we're going to have to multiply this whole reaction by 2. Okay? So let's multiply the first reaction by 2 to accomplish this. And we did. Okay, so now we have 2 waters yields 2 H plus and 2 OH minus, and we multiplied it by 2, so now we have positive 111.8 kilojoules. So now it looks like we should be okay with calcium, 2H2O, we have calcium 2 plus, 2OH, we have H2. I think we just add these 2 up now. I think we're ready to add them up and get the complete enthalpy of reaction. Okay. So when we add them up, we get minus 431.2 kilojoules. All right, so there are some practice problems on the worksheets about this, and I would really recommend going through all of them and practicing them over and over again because they're really, it seems kind of confusing when you first start, but they're really kind of fun once you get the hang of it. They're like little puzzles, and there's definitely going to be one on the test, so just get used to doing it. It's one of the easiest kind of problems that you can do. All right, let's go on to the next section, which is standard enthalpy of formation. Okay, so when we say standard state, it's different. It's not the same as standard temperature and pressure that we used with gases. Standard state is a different form that we use when we talk about enthalpy, okay, when we talk about thermodynamics in general. So that's 1 atm and 25 degrees C. If you remember, STP was 1 atm and 0 degrees C, so this is a little different. Just know that there's a difference. So standard state is 1 atm and 25 degrees C. So if we measure a property at the standard state, we put a little degree superscript there. Okay, so when we say that the standard enthalpy of formation, we can look those up in a book. The standard enthalpy of formation is the enthalpy of reaction when 1 mole of a compound is formed from its elements in their standard state. Okay, so we can look those up in a book, and we can use those plus Hess's Law to do all sorts of really fun things. So this is it has a lot of things. It's the delta H, which is the enthalpy of formation, but it's standard because it's got the little degree super sign, and it's a subscript F, which means the formation. So that's when it's formed from its elements in their standard state. So what that means, the standard state and formed from its elements, you have to remember that elements can exist sometimes in more than one physical state, right? So this gives you an example that carbon can exist as graphite or diamond, and oxygen can be O2 or O3. But we need to always keep in mind the reference form. That's the most stable form, so we wouldn't really consider oxygen to be O3. We would consider it to be O2. And that's the reference form. So as long as when we're making sure that we have our enthalpies of formation, as long as we have everything in the reference form, then we can use it for standard enthalpy of formation. So the standard enthalpy of formation for liquid water is going to be the enthalpy change for this reaction. And the reason this is a half of O2 here, instead of 2H2 and 2H2O like we normally say, is because we're saying that we're forming 1 mole of liquid water. The standard enthalpy of formation is when you form 1 mole of the substance out of its elements in their standard states. So standard state of hydrogen is H2, standard state of oxygen is O2, and we're only forming 1 mole of this H2O, so we can write this delta H with the subscript F and the superscript with the degree sign there. That means it's the standard enthalpy of formation. And you can look these up. But what's really useful when you look these up is you can use them. Okay, so we can calculate the delta H, which again it says DH here, for any reaction with one equation. And this is so easy. Okay, it is the sum of the delta H of formations, right, the standard enthalpy of formation for all the products, minus the sum of the standard enthalpies of formation for all the reactants. Okay, and this is because it's a state function. It doesn't matter how you got there. It only matters what you start with and what you end with. So if you notice there's an N in here, and what's N? That's just the number of moles. So we have to make sure to keep that in mind when we add all these up. So let's show you an example. Oh, and one thing to keep in mind. If an element is in its standard state, like oxygen, then when you say it's formed from from its elements in its standard state, if you have an element in its standard state, that standard enthalpy of formation is always going to be 0. Okay, so that's pretty useful to know. All right, so let's look at an example here. We have methane gas plus 4Cl2 yields CCl4 in its liquid form. And it's important to note the states here. Plus 4HCl in its gas form. And we want to know the delta H, the standard enthalpy of formation. Okay, so all we do is we look. Now remember, we have to do the products minus the reactants. Okay, so here's our chart with all of them in there. And you notice that Cl2, that's chlorine, is 0 because that is in its standard state. Chlorine is one of those diatomic molecules. And it is just in its standard state already, so it doesn't have to be formed. Okay, so all the other ones have to be formed, and we can look those up in a table, and we're going to use those to make this calculation. Okay, so we take the number straight from the table. 1 mole of methane times the minus 74.87. Say it was minus 74.87. Plus 4 moles of the chlorine times 0, because chlorine was 0. And then we do over here, we have the products. The products. So we have minus 135.4, which we got right out of the table, and 4 times minus 92.3. So that's right there, minus 92.3. Now we're calculating these all separately because this added up is minus 74.87 and this added up is minus 504.6. But if you go back to the equation, it's the products minus the reactants. So you have to be careful of that. You can't just do this and go this minus this. It's the products minus the reactants. Okay, so you have to take the minus 504.6 and then subtract the negative 74.87. Now be careful with the negatives. Just make sure you put it in your calculator the right way, because when you subtract the negative, you're actually adding. So you end up with minus 429.73. And that's it. All you have to do is just add these numbers up. Okay, the number of moles times whatever was in the chart. And make sure that when you match them to the right states, because sometimes you'll see H2O liquid or H2O gas, and you have to pick the right one. Okay? So that's how you do this. These are very, very simple problems. There's a couple of these on the worksheets as well. So I think that you'll find them pretty easy to do.